continue our journey into chapter 20 called DC circuit. You may be wondering, what is DC circuit stand for? Well, DC circuit is just a type of circuit. There's only two types. Direct current is what this thing stands for. Direct current. That means in a circuit, if your battery is like that, the current only flow one way. Because there will be circuits that we'll learn later in A2 where the current 1 minute is clockwise, 1 minute is anti-clockwise, so the positive and negative keep on switching. But that's for later. Now, direct current circuit, we are going to use all the thing you know from chapter 19, current of electricity, all those knowledge, level up, and apply in different, many different kind of circuits. Sometimes they look very strange because they're like a puzzle. Anyway, what's the goals? Okay, so previously, actually these two topics are from chapter 21, but we already learned it in chapter 19. So if you are kind of forgetting how they're like, go back to chapter 19, take a peek of it, okay? Oh well, it's under chapter 19 because they are kind of basic stuff. How's the difference between PD, EMF, and what is internal resistance? Okay, so that's that first part of chapter 20 we're done with already. What we're going to learn is in this video is what we call Kirchoff's laws. Now, Kirchoff's laws is not something new. Not some new. Because we know the concept, we just didn't put the name to it. So this guy is a German physicist or German fella. Okay, I don't know if his name is supposed to have 2H or 1H, or is it pronounced Kirchoff or Kirchoff? If you know German, you probably know better than I do. Hopefully. Anyway, this guy, he looked at the electricity patterns like we did, and he decided to name the electricity after his own, the patterns he see after his own name. So he's the first one to do it, so he got the name. But it's nothing new. We'll know what these laws are in a little bit. And at the end, hopefully, there's also going to be a part 2, like more parts after this video. We're going to use Kirchoff's law to solve circuits that may not be as simple as what we are used to. Because normally we like this, one loop, done. But what if your circuit looks like this? Loop here, loop here, loop here, got resistor here. What else? Come down here some more. Go like that, come up some more. Wow, then how to solve already? See, here got 1 loop, 2 loop, 3 loop. This is when applying or extending Kirchoff's law will be useful. Okay, so hang tight. Let's take a look at Kirchoff's laws. The very first law has to do with conservation of charge. Let's look at a very quick animation here. Okay, when you have a circuit, at any point, let's say this light bulb here, you have the same amount of current going, same amount of current going out. Obviously, because the Coulomb come in, it cannot just disappear. It has to go in. Then it has to come out eventually. You can't just create or destroy charge. So if you have something like a complicated circuit like this, you know this up there, right? The amount of current going in to that part is the same amount as all the little exit channels. Same amount now because you have to have the same amount of charge inside the circuit. So here go in so much means here plus here must have the same amount coming out. Okay? Logic. So Kirchoff came up with this law that basically just describes what he sees. And the law goes like this. Based on that thing we just saw, the sum of currents into a junction. Junction is an important idea here. Is equal to the sum of currents out of a junction. Well, hang on to the second statement first. But what does this mean? Sum of current into junction, sum of current out of junction. Just now we look at this one. You see here, let's say here got how many amps? 3 amps lah. 3 amps, wow, very big. Everything will explode. Never mind. Just I create numbers on it. Then here, exit will have, okay lor, let's say they're all equal because the light bulb is the same type. 1 amp, 1 amp, 1 amp. 3 amp go in, 3 amp go out in total. So you can use this idea for basically any kind of circuit, even if it's weird one that looks like this. So let's say you have wires coming in, wires coming out. This is what we call a junction. Any junction in the circuit where different wires join together. Okay, like T-junction on the road, you see when the road come here, suddenly got left, got right, got middle. That's what we call a junction. So if you have a junction, your current coming in, the first one is say 10 amps, woo, very big. Second one is 20 amps. What would be the current coming out here? I3. 10 come in, 20 come in. So how many come out? So 30 amp must come out lor. If not, where all these charges go, they cannot just disappear once they go inside a junction. Okay, so what this means, okay, sum of currents into junction, you can rewrite it as sum of currents in, which is your 10 and your 20, equals to your sum of currents out of junction. So whatever is out, only got 30 out, okay? In and out. Done. This is also linked to the idea of conservation of charge. Conservation means your charge cannot just be created, cannot just disappear like that. So it has to be conserved lah. All the charges in the circuit, they cannot just vanish. The second one, algebraic sum of current in junction 0 is basically the same thing. But it's talking about now you have current in. Let's say in, this means current out is negative equals 0. So all add up together must be 0 lah. But usually this one is more troublesome because you have to think of positive, negative. Oh, in is positive, out is negative. Can also, but it's more convenient to just think of in equals to all those out. Done. This one you may think like, Miss, this is a new thing that I don't know. Hey, you know already. Remember when we have parallel circuits, if they split like that, okay, if the current here is some value, then here split to become, what shall I say, 1 amp, very big, wow, 2 amp, then what will be the current through the battery here? Something split into 1 amp, 2 amp, so this one must be 3 amp lor. It's the same thing that you know, just that now there's a name to it and a proper equation that describes what we are seeing. Now let's go look at some practice questions to help us understand this idea better. Here on page 35 is a question to get us started with currents. You know, current will split, but how is split? Look at this circuit. Oh my. The diagram shows current 1, 2, 3, I1, 2, 3, 4, 5 in different branches of a circuit. So now we call them branches. Which equation is correct? So you look at this, you kind of like stun there for a moment. I. How to know? First thing, you want to remember the keyword junctions. We want to look at junctions, right? Because, you know, Kirchoff already gave us a clue. He said, I have studied many circuits and sum of currents into a junction is sum of currents out of a junction. Which means, first thing you need to do is you need to choose a junction to look at. Maybe you say, oh look, Miss, can I choose this junction? This is where the road split. Yeah, the main current is I, but there's no big I inside there. So maybe we won't choose this one. Okay, let's look, and maybe not this last one also lah. So got two junctions to look at. Okay, let's look at this one. So I choose that as my junction, and I see what is coming in, what is coming out lor. So sum of current in equals to sum of current out. So what's coming in? You have I1. Anything else coming in? No more. Okay lor. Then what is going out? I2, I3. That means I1 or split into I2 and I3 lor. Go, suddenly split. And that's literally what this equation says. So from there you can really go through, look at the answer to see which one matches. But let's look at this other junction down here as well. So if you do the same thing, sum of current in equals sum of current out. What do we have here? Then I have appeared again. So in, what is going in? I3 is going in, plus what else? I4. I4 is going in. What's going out? I5. So you put I5. iPhone 3, iPhone 4, iPhone 5. Okay. And that is how you can do. So you can just rearrange all of these things if you want to low. You want I3 equals to I5 minus I4. But I have no need to rearrange. You see the answer here, all positive one. So here you have two equations already. So you have to see which one is correct lor. Is there I1 equals I2 plus I3 anywhere? Oh yes, there is right there. The others are not quite right. Is there... It's wrong. I3 plus I4 equals I5. I3, no, these are all wrong. So this is your answer. Just pick a junction, check what current is going in, what current is going out, and then you can actually form an equation. Before I go on to Kirchoff. I cannot decide whether to say Kirchoff or Kirchoff. Anyway, Kirchoff, if you hear me say differently, just, you know, I mean the same thing. Before I go on to Kirchoff's second law, here's a, I want to give you a heads up of this strange current kind of question. It's on page 31. I'm going to flip over and try that. This one is kind of, it doesn't really fit into any topic. It's kind of just you have to think about current as a whole, common sense kind of thing. So here you have a 4-terminal box. Like, you know, in your house got a lot of box with wires inside. Connect to a battery and 2 emitters. Emitter here, emitter there. This emitter 1, emitter 2. Currents in the meters are identical. Which circuit inside will give this result? So you look at this, you're like, wow. If you just say I draw A inside here, it's going to look something like this. So what is going on here? It's going to be a very strange mess. But when you see this kind of puzzle question, I think it has repeated at least twice. I can't remember. You just have to think of the clue they give you that the current is identical. Means if somehow you split inside, this is everything joined together. So I think, wouldn't that be the best if you don't split the current? You just go direct and then like that. I mean, of course with resistors if not you short the battery. Yeah, that makes sense because here you didn't split anything, then you come here. But if you come inside here, then you split and do like that, means, your A2 is quite smaller already because your current will split. Okay, like what we saw just now, split. So now, if you want current to be identical, you gotta have them the same. Maybe you put a resistor here or here, okay? Then you look through, okay all this will split the current. This is the only one that does not split. So for your current to be identical, this sounds like the best choice. So if you ever see this circuit box question, and you see they're saying the current identical, don't overthink it. Identical means you're not going to split any paths. You're not going to create any junctions. Just keep going in the same one loop. Okay? Let's go and take a look at Kirchoff's second law now. Just now, Kirchoff's first law is about conservation of charge. Now, Kirchoff's second law is conservation of energy. You say, Miss, this sounds like chapter 6, work, energy, power. Yeah, same idea. We already have a look at it earlier already. Energy cannot be created or destroyed. So if you have so much energy, there is only so much you can use. So if I have this picture, good old animation, if your battery gives you, okay, this one we consider, this part is battery PD lah. If your battery PD is only so much, then the total PD that you drop for this light bulb all have to be the same. Okay, so you have 3V here, then you have 1V, 2V, 3V. All these add up together equals to the total that your battery has. And that is literally what Kirchoff said. He observed this and he said, the sum of EMF equals sum of PD around a closed loop. Here they use the word EMF because usually they consider internal resistance as another resistor. So let's say your battery has internal resistance, okay add another resistor that represents that internal resistance. So just look at the EMF. Sum of EMF equals sum of PD around a closed loop. Just now we talked about junctions. Now we're looking at loops. What is a loop? Loop means you start here, you go one round, you come back. That is a loop, lady. A closed loop. And this is the simple circuit that we've been looking at so far. What if there's something more complicated? Like this. Got parallel lines one. How leh? Let's go and see. Okay? So here if you have all these charges moving up, you see all the coulombs at the battery side, right? They suddenly get energy, then they go up. That's thanks to the EMF. So EMF, if you're going from the negative to the positive side of the battery, you're going up. Plus EMF. And then you go down, down, down. This one is when you're going through a component. PD across a component. Okay? So here they're just illustrating the amount you go up has to be the same amount you come down in the closed loop. So this is a loop already. You start here, go up, come down. Loop, loop, loop. Okay. So we'll leave those complicated ones for another time. Back to this point. See here we have EMF up. Then, well, this is parallel. So you can say this is one loop. Okay, and in this loop, you drop a certain PD, which is the same amount as your EMF. Okay, so how you can summarize this in terms of a kind of like an equation almost. They use a sum of EMF, sum of PD, all those. You can write it this way. You say the sum of EMF equals to the sum of potential drops. Or because if you say like, I don't want to write PD, means can I use something else? I can. Then you say sum of V lor. V here represents the potential difference across each component. Or you can say sum of E equals to sum of IR. Because IR is V. Okay? So when you talk about loops, let's check all the loops. The first loop, loop number 1. I need to change the pen color so I can see. Red color can? Can lah. Yeah, cannot also. Yellow. Let's do this. Yeah, that's better. So loop number 1. Then you have loop number 2. Then you have, maybe you start from this point. Loop number 3. And then you can have the major, you start on the battery, you loop number 4. Can also. Okay, so I'm going to look at loop number 4 because that's the one which is most directly relevant here. Loop number 4, actually got more loop leh. Draw all. Loop number 4 from the battery, loop number 5, loop number 6. Basically just trace all the paths that has EMF, PD, everything. So first things first, if you want to look at the EMF thing, no matter which light bulb you go through, which loop you take, if you're going from the battery side, you have some EMF E. That's the only one battery, right? No other battery inside circuit. Equals to potential drop across any of these light bulbs. So it's just V. So V, my equation very short now. Just one component. I will see more with more stuff later. Then you may be wondering, Miss, if I take, let's say, loop 3, for example, I start in this top left corner. Can also use this? Can. That one you have to think of it in a little bit of a different way already. You start here, you go down the mountain, then you go up the mountain. So, we kind of have to rearrange this as sum of E minus sum of V equals to 0, those kind of stuff. So, you have to start from here. If you say, okay, I go down the light bulb, so I minus V. Then, I want to go up the light bulb, so plus V. And that should equal to 0 because I come back to the same point. Okay, let me highlight the road I'm taking. I'm looking at this path now. Okay, I go down the light bulb, then I go up the other light bulb. So, down, up, back to the same point, 0. That's also the same idea in Kirchoff's law. You might be saying, Miss, isn't this obvious? Minus V plus V, 0. Yes, but make sure you know your basics because when you come to more complicated circuits, these are the same ideas, just a little bit more complicated. Let's look at this first one from page 51. I want you to see how you can solve it first. Don't do the whole thing, the whole thing is a bit long. Just do until this part 1, apply Kirchoff's law to determine resistance R. Take about 5 minutes to try through it. Okay, the first part you kind of have to remember and write what is the definition of Kirchoff's laws. So yes, 5 minutes, pause the video if you need more time or if you think like, Miss, I can write this in light speed as you talk, I can solve. Okay, sure. But yes, go try this out first. Give yourself maximum 5 minutes. Let's see, Kirchoff's first law. The best way is to talk about this. Sum of current in equals sum of current out. Where? At a junction. But don't write this out, write a sentence. Okay. So you want to say the sum of currents in to a junction is same as sum of currents out of junction. Sometimes the mark scheme will be more picky. They will say you must have sum of currents, only you can get. But sometimes they are inconsistent. Year to year is a bit different, but you just follow the strictest one. Also, make sure you write sum of currents, make sure you write junction also. Otherwise, say sum of currents equals sum of currents. What does that mean? Be specific. So, B1. Then the second one, they say Kirchoff's first law is linked to the conservation of something. Currents, right? Charges come in. same amount of coulomb come in, same amount of coulomb must go out. So that means the conservation of charge. Charge cannot be created or destroyed. They are just there. Kind of thing, no? Okay. Charges, each charge electron. Wow, if charges can be destroyed, our world is ending, man. Or we would have found a way to destroy our world. Anyway, this one. Variable resistor of resistance R is used to control the current. Yep, variable resistors like rheostats, potentiometer, these are used to control current because that's the only how else we're going to control current. You either change the EMF or you either adjust the variable resistor. Here you have a generator G, so it's also creating electricity here. That's why you see got plus minus is a battery. EMF 20 volt internal resistance. Current in circuit 2 amps. Let's draw the current. Label it. Here you might be wondering, is the current like that down or up? How you know leh? Actually, it doesn't really care in this case. But if you really want to know, this one, the EMF is bigger. This one, the EMF is smaller. So it's going to push. The bigger one's going to win now. It's going to push the current in an anti-clockwise direction. Zoop, zoop, zoop. Anti-clockwise like this. Anti-clockwise. Now, how do we solve? What are we looking for here? We're trying to find the resistance R. And you got two batteries here and you want to apply Kirchoff's laws. But the second law, okay, not the first law because there's no junction here, so your first law is pretty much useless. Current is the same everywhere in the whole circuit. But Kirchoff's second law, sum of EMF equals to the sum of potential drops in the whole circuit. Let's not do the one where it's like equals 0 because that one you have to think of positive, negative, which one is which. Okay, so EMF. Let's check the EMF first. Let's say I start from here, follow current direction, and then I move. I check in that direction. Go to this one. Okay, so you have first EMF here. You're going from negative to positive. So you're going up. Okay, so you have 20. Then you come down to this second battery. Here is the positive, here's the negative. Oh, you're going down now from positive to negative. So down 12. Then go back to the original. Okay, can I do that? If you're wondering why negative, well, we just say you go up and you come down one of these. Or you can think of these two batteries are fighting. So they are kind of cancelling each other out. So 20 minus 12. But it's better to think of up and down. Up potential and then down potential. Then what else? Sum of PD. Okay, so what are all the resistors here? Let's also start from this same point. Let me highlight it. Start from here because you need to start looking from somewhere. So you have the current 2 amps passing through the first 0.5. So here you're going to have a PD already. So that will be current IR, V equals to IR. So current times resistance, IR. That's the first potential drop. Then you go. Oh, there's another one. Go around the loop, come down here. Here's another potential drop, V2. I should label them. So you just add together. Current is 2 amps, 0.1. 0 ohm. And that's it. Is it? Oh, one more. Don't forget the R we're trying to look for. So go. Here, this another potential drop, V3. So let me just write that down. That will be current times resistance. I don't know, R. From there, you can rearrange to find your R. So 20 minus 12 minus 2 times 0.5 minus 2 times 0.1. Yeah, by 2. 3.4. 3.4 ohm. No SF, right? This is 3.40. Okay, 3.4. So 3.4 is the potential drop related to the potential drop across R, and you can first do 3.4. So done lor. How many marks is this? 2 marks. Okay, so probably is one C1 here, A1 here. Let's check. Is it? Yes, it is. Okay, so what we just did here was summary. Sum of E equals to sum of V, which is just IR, across the whole loop. This is considered one loop. Okay, so not too hard, just go one by one. Just be careful the battery side. You have this negative, positive kind of thing. Okay, here's another one, a MCQ question now, but look at that. Look at all those branches. I want you to try, see what you can do about this. It just takes a wild guesses. A, B, C, D, ma. You choose one, 25% chance you'll get it correct. Even if you didn't know how to do it. So here you have a DC supply connect to a circuit, 5 resistor. Potential drop, whatever is given, it already written there. What are the potential drop across M, P, and Q? Ooh, try solve this puzzle. It's like those Sudoku puzzle. They give you a few numbers, you have to find the rest. It is possible. Hint, use Kirchoff's law to draw loops if you can. Okay, give yourself some time to try this one out. 2 minutes or something like that. Okay, pause the video. Okay, let's look at this thing. Potential drop, they gave us choices. Okay, but let's just zoom in a bit. Oh my, what happened to my screen? There it is. Now, how do we find the missing potential drop across M, P, and Q? You may think of our old school way. You say, Miss, these two lines are parallel, right? This line and this line. Yeah, they're parallel, so you could say this whole thing, potential is 20 volt. The potential across PQ is also should be 20 volt. You could say that, but it's better to start thinking in terms of Kirchoff's law now. Because that idea is where it's originated from Kirchoff's law. What do I mean by that? I mean, you take a pen or whatever, you trace a loop. Let's go with the outside loop first. Loop, go back to the battery. That's called one loop. So in that loop, you go up by 20. That means you drop by 7 and then another drop here. I don't know why I say I call it VM. Then done already lor. So 20 equals to 7 plus what? 13 lor. So your VM have to be 13. That's how you can solve the first one. So if you look there, you see 13. This one out. This one out. This one correct. Okay, done. Then the other ones. Think of loops. The reason why I say think of loop is because there's this funny shape inside here. Okay, so I rub off. Okay, where's my eraser? Okay, so this one is 13 volt drop. Now the inside one. If you just take this loop and then say, Miss, I just do like that lah. Cannot, you got two unknown, you don't know P, you don't know Q, so cannot. Choose a different loop for now. What else can you solve? Well, you could do this one. Maybe you start from here and then you go like that. This one you have to think of a little bit of a strange idea already to see what is this thing. So you start off with a 7 drop. This one no EMF, so you think of 7 drop. Okay, 7 drop. 4 volts drop. Drop some more. Then here you want to go up plus V. And then because you go back to the original place, so 0. This is a variation of that one. Or you can think of it this way. 7 plus 7 equals to VP. Or the one that go down and then all the one that go up. So check and see. Did I write 7? 4. Sorry. This is supposed to be 4. Because here is 4. 7 plus 4. Okay, so what is VP? So here VP should be 11. So you go down. Then you see. Where is 11? 11! Nice. That pretty much narrows it down to one answer C. But let's also look at Q. Good practice for this thing. Oh, also, you might be wondering, what means why can minus plus? Okay. That's because you think of it this way, you start with 20 volt potential. So at the top of here is 20 volt. And the top of here is 20 volt. So once you go across here, you already drop by 11. Go across here, you drop by 7. Then you drop some more by 4. So 20 minus 7 minus 4 is 20 minus 7 minus 4 is 9. So at this point, your potential is 9 volts. So 20 minus 11, check and see. This is 20. 20 minus, did I write N? 11 is 9 volts. So correct, that's how you check. your potential is dropping, and then the 7 volt is the drop across that resistor. You can do it for here, basically any point on the circuit. Okay, that's a very important idea to have. Now, what's the last one? Q. Come, we look at Q. Q have many choices already. You can pretty much draw any loop as long as it involves Q in it. Let's practice the one where you have to do not the EMF one. The EMF one easy lah, you just draw like that. All the EMF equals to potential drop. But let's look at the other idea where you have to kind of start at the place and then you go like that. So you zoom in on that one loop only. So let me write out here. So here you're at potential of 9 volts. At the top part, you're at a potential of 13 volts. So you drop 13 somewhere, here becomes 0 volt potential already. So here, you're already going back to the battery, so you should be at 0 potential. So 9 volt, to go 0 potential, you need to do what? Minus 9. So 9 volt drop. So I'm not even using the equation, I just look at it. Okay. If you want to do the equation style, can. We start from where? Just choose a point lah, here lah. The X here. Which way shall I go? Any way goes, doesn't matter. Let's go up this way across M first. So then you're going up the hill. So you have to plus 13. Then you drop, you go down by, is that 4? I can't see, I draw too much over it. 4. Then from Q, you're going down some more, 9. That one is what we're trying to find. Down by some value, yes. Equals to 0. Should be 0 already lah. So V equals to 13 minus 4, which will give you 9. Yep, 9. There we go. So many ways to do it. You can think of potential, all dropping. And that's it. So yeah, the answer is C. Ding, ding, ding. Let's look at this interesting question on page 19. This one, I will say, please try out, must try out. If you need to take a break and go to sleep, wake up and continue, also can. Here you have a resistor, all identical. And ammeter negligible resistance, so they don't have resistance, okay, good lah. Reading on ammeter 1 is 0.6. What are the reading on other ammeters? That's all the info they give. Wow. Look at this circuit. Loop and loop and loop. How? Well, the first step I'm going to do is, this looks a bit crowded. I am going to redraw this thing. So maybe I will do something like that. There's a resistor here that's R and the resistors that are. So I combine those into 2R. Okay, that's the first loop. Then you have battery. Then you have 1R. Then you have another, got 3 here, R. So in that loop, I can basically combine that into one resistor with 3R resistance. The R I just create lah, because I know they're identical, so each one will be R lah. Okay, so I redraw already. Now what? Try this one out. Don't give in quite yet. And I want you to think about this. You see, they're asking about current, right? So should you use Kirchoff's second law or Kirchoff's first law? Which one will be more helpful for you to solve this? Think about it. Think hard about it. Draw loops lah, write equation, everything. Okay, I'm going to label the currents now. I2, I think that one. Then here is I1. I'm lazy to draw ammeter, so I just label current. Okay, so it's like a water fountain like that. The middle go up, the side all come down. So current will split and then go down to I3 and I4. If you're curious what this one up here is, this is I3 plus I4. Because they haven't split yet, later only they split. This one here is already I1. But nah, we don't need to worry about those. First things first, how are we going to do this? If you try Kirchoff's second law, you'll find that you have too many unknowns. It's not second law, Kirchoff's first law. Because you say, okay, miss, so I2 equals to This is the main one coming out from the battery. I1 plus I3 plus I4. That's not very helpful because you don't know, you have too many unknowns. How? Well, the most you know is I1 0.6. Well, you could make a whole bunch of unknown equations. Let's see if you can do that. You will need, at this rate, you have 1 unknown, 2 unknown, 3 unknown. So you will need 3 current equations with 3 unknowns. Then you solve simultaneous equation. A lot of work. Don't want lah. Don't want. So Kirchoff first law not very helpful now. Maybe later it will be useful. Let's use Kirchoff's second law to help us a bit. The thing that we know is here is 0.6. Okay lah, so we start with that, 0.6 amps. Is that 0.6 amps? Yeah, they told us here. So let's start with this loop. Let's go with the battery. Come on like that. I call that the first loop. Loop number 1. For loop number 1, what do we have? You have going up by a certain battery potential. I don't know what is it leh. PD across battery I just call V lah, whatever it is. And then you have 1 potential drop. Some current, I1, times your resistor, 2R. If you haven't combined resistor, then you have IR plus IR lah. Okay, this one we know is 0.6, so that's convenient. But we don't know the rest never mind lah, just put. So your V will be, what is 0.6 times 2? 1.2 R. R is a constant. Okay lor, we leave it as that. But we'll use this some more. Now we know that the PD is 1.2 R. Let's choose another loop. Let's use this loop leh. Loop number 2. Can try and see. Come, loop number 2. So loop number 2, you're going up the battery, only 1 battery. Then you drop I3 times R. But very conveniently, you already know the battery PD at first is already 1.2 R. So you just write 1.2 R. Oh, 1.2 R. The R and R can cancel out. Yay! You divide both sides by R, so R is gone. So then I3 is just 1.2 amperes. Ooh, very nice. That was a trick. We didn't know V, but in the end the R cancelled out. So you need to see I3 or A3 is 1.2. Wow, so easy. You already straight away find the answer. Okay lor. But since we're not in normal exam, you find you're confirmed this is correct, you just circle D already. But since now we're problem solving, let's might as well find the rest. So we can convince ourselves. But in exam, you don't have enough time to do all this lah. Next one. You draw a loop. Oh, wait. I need to draw here. Loop from the battery up. This is loop number 3. Number 3, no more space, so I write on the left side. Again, you have battery up, V equals to I4 times 3R. But again, your battery, you know, the equation for it is I3R, I1.2R. So divide both sides by R. I4 is, 1.2 divided by 3, 0.4 ampere. Correct. Although this is a tricky question, you see, you get 1 correct, confirm you already know the answer already. Which is good lah, because they know you take a lot of time. What else do we have? A2. Oh, A2. A2, you can use, this is where you can use Kirchoff's first law. Because you know that here your current I2 will split into I1 and this one is I3 plus I4. Split into everything. So if you know all the currents, you can just add them all together. So I2 will be I1 plus I3 plus I4. I1 is 0.6, I3 is 1.2, I4 is 0.4. So what is I2? Let's check. Dun, 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 dun. It is 2.2. Yay! So this is how you can solve one by one. The question is, Miss, if you don't solve one by one, you can just straight away check the answer and know. The answer is maybe. If you apply your Kirchoff's first law, this one, to every single answer, you will realize that it's true for every single answer, so something wrong, so you cannot use. In this case, I cannot use. Sometimes the answer may give differently otherwise. Okay, I'm kind of blocking the amps behind me, but yeah, I wrote amps. Okay, to close off this video, let's look at the final structure question that is similar idea. This is page 80, the last one. I want you to try, not the whole question, it's a bit long. You can go and try after you watch the video. But for this video, I want you to pause and try up till the left side page. So until part 1. Part B1. Yeah, just part B1 is okay. How many marks is this? 2, 3, 4, 5. So if it's a 5-mark section, mark, roughly 1.25 minutes per mark. So how long should you spend on this? 5 times 1.25. Take a maximum of 6.25 minutes. 6.5 minutes. Okay, mark per minute. So take maximum 6-7 minutes-ish. Try out from A until B1. And then we'll go through it together. Pause video lah. Try first. Something wrong with my mouse keyboard already. Oi, oi, oi. Okay, Kirchoff's second law. Hopefully you can try and remember what is it. Second law is the one with the PD one going up and down. So that one, how are you going to write it out? You can say the sum of EMF equals to the sum of potential difference or voltage drop, or you just say PD lah, around a closed loop. Closed loop is important. Yes. Full stop. Ding ding. This is a... Ooh, this is not a B1 mark. Let's look at the mark scheme. You see the mark scheme here? Okay. Ooh, that's a little too big. Never mind. When you see an underline, right? This underline basically means you must have the word sum. So if you just say EMF equals to PD, no. So you must have sum of EMF, sum of PD. And then you must also talk about around a loop or closed circuit. Oh, see, they're very specific now. 2 marks there. One is the M1 and then the A1 mark. What does that mean? Okay, let's see. So let's check and see. You have a M1 mark if you talk about sums. If you said sum, then only you get your A1 mark when you talk about loops. A1, M1 is linked one, okay? So 2 marks in total for this. Now we come to the circuit part. You have a circuit, okay, as is seen. Negligible internal resistance. Yep, usually makes life a little easier. And they tell us all the resistance and they label the circuit. Okay, resistance of Weber resistor R is changed until the voltmeter in the circuit reads 0. That means there is no potential difference between here and here. That's why the PD is 0. That's just what it means, lor. So you can kind of treat that as a branch, kind of. Yeah, you could treat that as a branch. So you can make 1 loop, 2 loop, 3 loop, quite a lot of loops. But how to find your current? Well, you could say, Miss, can I do this loop? Yeah, but you have 2 unknowns. You don't know current, you don't know R. So if you include R in your loop, you won't be able to solve part 1. So we need to choose a different loop. If we choose this loop, we still have the problem of we don't know R and I, 2 unknowns. So we have to choose this loop now. Okay, let's start with that, shall we? So you have to think of, there's many batteries here. Let's scroll down. Okay, so for this loop, you just start looking somewhere. Current flow this way, right? Start from here, start from here. Check, what's the battery? There's 1 battery here, 6 volts. Okay, so just 6 only lah. Then what are all the PD drops? Just 1 only, so V equals to IR. This one, the voltmeter does not have a PD drop because it's PD 0. So it's basically just a wire connecting. Okay. So you have PD, we're looking at PD only, I times 4 ohm. That's all. Hey, you see this one only 1 mark. Don't overthink it. So I equals to 6 divided by 4, that's just 1.5 amps. So 1.5. Straight away, you give A 1 mark if you got correct. So yeah, this is kind of just V equals to IR. Although you can add the sum of V equals sum of IR, but no point, only got one component, one battery. Okay lah, never mind, this part still very chill. Then you have to find the resistance R. Now you need to choose a loop that includes resistance R. There are a few ways to do this because you can see why we can choose different loop and get a different thing. But what I'm going to do is I'll show you both lah. I'll do the working up here so you can see the circuit. First loop, if I choose the small one. If I just look at that small loop, I need to write what are the batteries. Only one battery, easy, just 6. Then all the potential drops. We know our current is 1.5 times R plus, what else? This one no PD drop. Oh, 1.5 times 1.5. So what is R from here? If you use that method, 6 minus 1.5 times 1.5 divided by 1.5. 2.5. 2.5 ohm. Okay, that's using the first loop, the yellow loop. If you want to use a different method, slightly different method, can also. Let's do the purple loop. If you want to take the whole thing, it's the purple loop. Can, you have more battery so you have to be careful a bit. So let's do the EMS first. Let's start from the bottom right corner. Go up 6 volts. And then here, from negative to positive, you're going up. Okay, so going up potential, add another 6 volts. No other battery? Okay, now we look at PD drop. I'm just going to shortcut and say the current I times all the resistors add together because I lazy to one by one write IR. So you have 1.5, the first one, plus R, plus 4 ohm. I think that's it, right? 1.5 R, 4 ohm. Okay, then you find R. In exam, if you have a lot of time or you do very fast, you do different method lah, check your answer. If you get something different or means something wrong somewhere. So this one also 2.5 ohm. So what is the 2 marks? First one is your IR thing. If you know how to find loop around PD, they'll give you your first mark. Why become blue color? Hang well. Okay, then the second mark is your 2.5 ohm. 2 marks for this. I'll transfer this down later. Okay, I'll transfer this down later. Okay, so check and see what are some new ideas that you didn't realize when you first try this thing. It's okay to write them down so that you treat it as a learning process. Great. So that's the end. Remember Kirchoff's first law, second law, what they are, and they are just observations of what we already know. But now you can apply to many different kind of circuit with many that looks very scary. Okay, so hopefully by the end, you know how to state these laws and apply to solve some circuits. In the coming videos, and basically all of chapter 20, you are just applying. So we're going to look at more applying of Kirchoff or Kirchoff law. Sorry, Mr. Kirchoff. I don't know how to pronounce your name. Okay, bye-bye. I'll see you in the next video about parallel and series resistors.